We all use large language models pretty much every day. But let's be honest, what's really going on inside that black box? Well, today we're digging into a paper that found a surprisingly simple way to shine a light inside. And trust me, the answers it found are probably not what you're expecting.
Now, this might sound like a completely impossible question, right? A model like Llama 3 represents every word as a vector with thousands of these numbers, these dimensions. But what do they actually stand for? Is it all just mathematical noise, or is there real, human-understandable meaning packed into a single coordinate like dimension 1280? Well, hang on, because by the end of this, you'll actually know the answer.
So, to answer that big question, we first have to tackle the core challenge here, what I like to call the embedding black box. These crazy high-dimensional vectors are the absolute foundation of how models understand language. They're everything. But they are also famously, notoriously difficult for us humans to interpret.
So what are we even talking about with dense word embeddings? Okay, think of it like this. Imagine a massive, multidimensional map where every single word has its own specific coordinate. Words that mean similar things, like king and queen, they're plotted really close to each other. It's an incredibly powerful way to capture meaning. But here's the catch. This map has thousands of axes, and we have basically no idea what most of them represent. It's like having a GPS that works perfectly, but all the street names are written in an alien language.
And look, this is not just some academic puzzle. This opacity has serious real-world consequences. I mean, if we're going to use these models in medicine, how can we be sure they aren't latching on to some random spurious correlation? When we're auditing for bias, how do you find those harmful stereotypes that are subtly encoded in the nooks and crannies of the vector space? And for anyone in advertising, how do you make sure your brand doesn't get placed next to toxic content if the model's idea of toxic is a complete mystery?
So how do we start to fix this? Well, the paper we're digging into introduces a method called top K activation analysis, or TKAA for short, and the authors frame it perfectly. It's basically a flashlight you can shine into the dark room of an existing model to finally see what's in there. And the real beauty of this method is just how simple it is. Seriously, you start with that giant embedding matrix, right? Where rows are words and columns are dimensions. Step 1, you just transpose it. You just flip it. So now, each row represents a single dimension's behavior across every word the model knows. Then, for any given dimension, you just ask a really simple question. Which words light this thing up the most? You just find the top few words with the highest values. That is literally the entire algorithm. The key here is there's no GPUs, no retraining, no complex labels. It's an incredibly lightweight way to start mapping a model's internal concepts. Okay, so let's go back to that question from the beginning. What does dimension 1280 of Llama 3 actually mean? Well, when the researchers ran TKA on it, this is what they found. The words that activate this dimension the most are function, void, import, class. It's immediately crystal clear. Dimension 1280 has learned to represent programming keywords. And just like that, the black box isn't quite so black anymore. We've just put a human-readable label on one of the model's internal concepts.
No, that's just one dimension. What happens when you apply this super simple method at a massive scale to a huge model like Llama 3? The researchers analyzed all 3,072 of the model's dimensions across more than 80,000 words. And the results? They were truly surprising.
And this leads us to the million-dollar question. If one dimension is for programming, what about the other 3,071? How much of the model's brain can we actually map out with this technique? Any guesses?
The answer is just 1.92%. That's it. Out of over 3,000 dimensions, only 59 of them could be clearly and confidently assigned a single, coherent meaning. Now, to put that in perspective, earlier work on smaller models suggested we could interpret maybe 30 or 40%. So this massive drop is a really stark and incredibly important finding.
So why is the number so low? Well, this quote from the paper really hits the nail on the head. It's because of a concept called superposition. The easiest way to think about it is like data compression. So instead of using one neat folder for your vacation photos and another one for your work documents, the model just crams them all together into one big, jumbled file to save space. It knows how to pull them apart when it needs to, but for us, looking from the outside, it just looks like noise. This 1.92% number is really the first direct measurement of just how aggressively a big model like Llama 3 uses this trick.
So what about that tiny fraction that we can understand? Well, this is where it gets fascinatingly weird. The vast majority, nearly 3/4 of the understandable dimensions, were just chemical suffixes, like ill. The model isn't a secret chemist. It just noticed a simple pattern in words. Another cluster seems to be a fingerprint from its training data, with a bunch of JavaScript terms like console and browser all grouped together. But the single strangest finding of all
was dimension 0033. This turned out to be the single, sharpest, most clear-cut, most monosemantic dimension in the entire model. And what does it represent? Divination, words ending in mancy. The fact that the most clearly defined concept in a multi-billion parameter model is a rare suffix for fortune-telling methods, that just perfectly illustrates the strange, almost alien way these models organize information.
Okay, so being able to label these dimensions, even the really weird ones, opens the door to a much more serious application. We can adapt this flashlight idea, not just to find concepts, but to audit for societal biases that are encoded deep inside the model.
This chart visualizes that. To do this, the researchers created what they call concept vectors by averaging the embeddings for groups of related terms, like a bunch of male-associated words versus female-associated ones. Then they just measured the similarity between those concepts. A high positive score, which you see there in red, means a strong association, and you can see it plain as day. The model strongly links age-old concepts with negative sentiment and female-associated terms with caregiving occupations. It gives us a concrete, quantifiable measure of the model's bias.
But we can go even deeper than that. You see, bias isn't always just about one concept being closer to another. Sometimes a model encodes bias by treating two totally distinct concepts as if they occupy the exact same region of its internal map. This is called geometric conflation, and it's a much more fundamental, structural kind of bias.
And this heat map illustrates that perfectly. It's showing the overlap of the top 50 activating dimensions for different concepts. Now, just look at that dark red square where age-old and sentiment-negative intersect. That value, 0.49, means they share nearly half of their most important dimensions. In the model's mind, the very concepts of being old and being negative are almost geometrically inseparable.
And this leads us to one of the most important technical findings of the whole paper. It turns out, not all biases are created equal. The researchers discovered that the gender and age biases were robust, meaning they stuck around no matter how you normalize the data. This suggests they are baked deep into the model's geometry. But biases related to race and religion were fragile. They would flip or even disappear entirely when you simply subtracted the global average. This means they were mostly just an artifact of the coordinate system, not a deeper structural link. And that is a critical distinction for anyone doing serious AI auditing.
So, stepping back, what are the broader implications of all of this? Well, this kind of analysis really affects everything from how we audit the models we already have to how we might think about designing the models of the future.
TKAA really represents one of two main paths we can take toward interpretability. It's a post-hoc analysis. It's that flashlight we can use on any existing pre-built model. That's incredibly valuable for auditing the systems already out there. The other path is interpretability by design, which is more like building a house with lights already in the walls from the start. It's way more costly because it requires training a model from scratch, but it can give you much deeper control. The key is they aren't competing ideas, they're complementary tools for different parts of the AI lifecycle.
And at the end of the day, this isn't just some research curiosity. This has immediate, practical applications. For auditors, it gives you a concrete, reproducible evidence base. For ad tech, you could build super cheap content filters by just flagging documents that light up known toxic dimensions. We saw how it can surface fingerprints of training data. And for anyone working with vector search, you could actually improve your results by downweighting dimensions you now know carry unwanted biases.
This work is a huge step forward in peeling back the layers of these incredibly complex systems. We can now put a meaningful human-readable label on about 2% of Llama 3's embedding dimensions. But that leaves us with one final, massive question. What secrets, what biases, and what incredible undiscovered capabilities are still hiding in the other 98%?